All right, good morning, everyone. Welcome to today's class. Today, we will continue to talk about Python basics. Last time, we talked about loops, for loops, and while loops. And today, we'll continue to talk about it. So in this small section, we'll talk about fine-tuning your loops with two keywords, break and continue. So let's first take a look at the definition of these two keywords. The continue statement skips the remainder of the current iteration and goes to the next iteration. So the continue keyword will end the current iteration of a loop. No matter it is a for loop or a while loop, it will end the current iteration. So it will skip all of the statements after the continue keyword. And the break statement will break out of the loop entirely, which means it will end the entire loop. Right? No more iteration anymore. Right? So let's take a look at a few examples. So first, I want to print a string of even numbers. So see, this is a for loop for n in range 10. So namely, n is in this a list somehow like this, all the way to 9. Okay. If the modulus of n divided by 2 is not equal to 0, then continue. Otherwise, print n. Okay. So if the remainder of n divided by 2 is not equal to 0, that means it is odd. It is an odd number. Then the continue keyword is there, is in the if statement. Okay? And because it is odd, this statement will be skipped. Okay? And this iteration will be ended. So which means if it's an odd number, don't print it. Okay? And in the next iteration, n will be even. And then this statement will yield a false. So then this will be skipped, and this won't be executed, and the even number will be printed. Okay, so that's it. So this is how the continue keyword works. Okay? Very simple. Let's run this. So this is the result. Okay, pay attention. The range function is sort of a list of numbers from 0 to up to 10, but not including 10. This is how continue works. It will end the current iteration. Then take a look at the next keyword, break. So I first define a variable is a character string, Merry Christmas and Happy New Year. Then I write a for loop. For letter in S, whatever the sentence is, if letter is equal to end, break. Otherwise, so break means it will end the entire loop. So essentially, this will help us to print out the first part of the sentence until it encounters the end operator or the sign. Okay, so let's run this. So see, as long as the program sees the break keywords, it will end the entire for loop. So nothing after end will be printed. So this is these are the two keywords that can be used to fine-tune your loops. Any questions? And they can be used in any types of loops, like for loop or while loop. All right, now let's see functions. So one way to organize your Python code and make it more readable and reusable is to factor out useful pieces into reusable functions. Basically, if you know that you will repeatedly run a chunk of code, it's better to create a function which contains that part of the code, so that next time you can just reuse it or call the function. And so we will cover two ways of creating functions, the DEF statement and the lambda statement. The DEF statement is used to create a regular function, and the lambda statement is used to create short anonymous functions. We'll take a look at each case. Before we talk about how to create a function, let's see how to use functions. We just call functions using parentheses. For example, print good morning. Good morning is a character string. Okay. We run it, we get the result. Okay. So we use parentheses to call a function. And in this statement, print is the function name, and good morning is the argument of the function. And sometimes you will use some keyword arguments. So in the previous example, good morning is just a regular argument. Notice that I didn't put a name of the argument in it. Okay. But sometimes you want to add some arguments with names. They are called keyword arguments. For example, I want to print 1, 2, 3, and at the last, I add a keyword argument, sep equals hyphen, which means the separator should be hyphen. So if I run this, you see the separator between any two values is hyphen. So this is called a keyword argument. And whenever we use the name of the argument, it is called a keyword argument. Similarly, we can add the and equals space at the end. So this is also a keyword argument. You print it in this way. Notice that whenever you have both arguments and keyword arguments at the same time, you always need to put the keywords argument at the end of the argument list. You notice that these two examples show you that, right? You always need to put the keyword argument at the end of the argument list. So this is a rule in Python. All right. Next, let's talk about defining functions. First, using the DEF function. So let's see one example. So this example will list n Fibonacci numbers starting from 0 and 1. So what is a Fibonacci number? If we start with 0 and 1, then starting from here, and the third number should be the sum of the first two. So it will be 1. And the first number is the sum of the second and third. So it will be 2. So you keep adding the numbers and yield the third one, the first one, etc. Okay, the next one will be 3. So this is a list of Fibonacci numbers. So we want to create a function to list the first n Fibonacci numbers starting from 0 and 1. So this is the function. We start with DEF. This is the keyword. And then the name of the function. We can just call it Fibonacci. You define it. You give a name to it. And then parentheses, the argument or arguments that are needed in the function. In our function, we only need one argument. In this case, because we only care about the number of numbers in the list. So we need n of them. And then create an empty list and specify the starting values, a and b. And then we use a while loop to repeatedly append new numbers to the list. Using this rule, we let a be b and b be a plus b. And then finally return L. Okay. So notice that we always use the return keywords to specify the value that is returned by the function. Then let's run this. We define a function. No output because this is just a definition. Now, after we define the function, we can use it right away. For example, we want to list the first 12 Fibonacci numbers starting from 0 and 1. Then you see we get this. So our function works. Okay, 0, 1, 1, 2, etc. Totally 12 numbers. And the multiple return values are simply put in a tuple. So in Python, you can create a function that returns multiple values, but they are, in theory, wrapped in a tuple. But we know that in Python, we can create a tuple just by separating them by commas, right? We don't have to use a parenthesis to wrap the values. We just need to separate them by commas. So basically, you can return multiple values. For example, we create a function to return the real part, the imaginary part, and the conjugate of a complex number. We can create a function like this. So the argument is called val. So that is the value of the complex number, the input. And then this .real method will extract the real part of the complex number. And this .imagine, this part will be used to extract the imaginary part. And last one, this method will be used to extract the conjugate of a complex number. Okay, so let's first define it, and then let's use it. Suppose the complex number is 3 plus 4j, then our function works. Okay, this is a real part, 4 is the imaginary part, and 3 minus 4j is the conjugate of 3 plus 4j for a complex number. So the key point of this example is you can return multiple values using a function, 1, 2, 3. Just don't forget to use comma to separate them. So essentially, you are returning a tuple with 3 values. Okay, so it's allowed, okay, it's permitted. And a side note about complex numbers in Python. So in Python, complex numbers are represented by x plus yj. Right? Notice that in math, we usually use x plus yi, but in Python, it uses j to represent the imaginary unit, square root of -1. Okay, just pay attention to that. So whenever you specify a complex number, you need to use x plus yj. Okay? X and y are any real numbers. All right, that is the function. And in functions, we know that there are arguments, and some arguments can have default values. For example, in the previous Fibonacci function, a and b, the starting values are fixed. They are 0 and 1. What if you want to give it more flexibility? For example, you can let the user of the function to define the first 2 numbers, decide the first 2 numbers. Then you can do this, specify a function, define a function, still called Fibonacci, but with 3 arguments, and a and b. A and b are the first 2 values in the Fibonacci number. But usually, to facilitate the usage, we usually give default values for some arguments. In this case, we can let a be 0 and b be 1 by default. So if the user doesn't want to specify the starting values, it's okay. If they want, they can change it. So these are called default argument values. So we can run this. So this is a new function with 2 additional arguments. Now, let's call it. Again, as I said, because a and b have default values, you don't have to specify them. For example, we can still call the function in this way, Fibonacci 12. We get the same list because by default, a is 0, b is 1. But you also have the option to change the first 2 values. For example, I want the list to start with 1 and 3. Then we can specify a equals 1, b equals 3. Then we get a new Fibonacci list. So whenever you create a function, you have the option to specify some arguments with default values to give the users more flexibility. And if you specify the argument names, then you don't need to follow the order of them, the default order. For example, we can also let B go first and A go second for the two starting values. So you can switch the order as long as you keep their names when you call the function by the same thing. All right. Then a small side note, flexible arguments, asterisk arcs, and double asterisks, keyword arcs. So sometimes you might wish to write a function in which you don't initially know how many arguments and how many keyword arguments you want to pass into the function. So you're not sure. In this case, you can use these two to specify them. So this will catch all arguments, regular arguments. And this one, double asterisk KW arcs will catch all keyword arguments. So let's see how they works in one example. We'll create a function called catch all, and it will catch. So it's a very simple function. It will print the arguments and keyword arguments, no matter how many we have in the function. No matter how many keywords argument and arguments are input into the function, okay, you will print it out. So let's first define this function, and then we call the function. So we pass 3 arguments and 2 keyword arguments into the function. So let's run this. You see, it will print the arguments as a tuple and print the keyword arguments as a dictionary. So basically, it's very flexible. You can, for example, let's see some more examples. So now we pass these two first. These two are regular arguments without argument names, right? The last one is a keyword argument. It will just print it in the way. Similarly, I just pass 1 argument and 1 keyword argument. We get this. Okay. So now let's zoom in. So actually, the names ARGS and KWARGS don't matter. So what matters? The sign or the operator that is ahead of the argument name. If the argument start with asterisk, that means it is regular argument. Okay? So that is part of the regular arguments. And double asterisk means keyword arguments. Okay, so you can give any name to it as long as it start with this one or this one. For example, you can make it shorter, like AG, KWAG. It doesn't matter. Python will take it. So a single asterisk before a variable means expand this as a sequence. So for regular argument, it will just take it as a sequence of values. And for double asterisk, it means expand this as a dictionary. So one previous example is very clear, right? So this is in the keyword argument part, right? It expands this as a dictionary. Key value pair is a dictionary. Similar here, key value pair. It create a dictionary for you. All right. Sometimes they are useful if you want to create a function but you are not sure how many arguments and how many keyword arguments you need, then you can use these two keywords. And the second type of functions are created using the Lambda keyword. So they are used to create short one-off functions. So let's see, anonymous functions. For example, I create a function, I call it add, okay, and call Lambda, and the two arguments are x and y, and then x plus y. So whatever before this semicolon are arguments of the function, the Lambda function, and whatever after this semicolon is the value that will be returned by the function. So usually just one line is a very simple, short, and anonymous function. So suppose it should be an anonymous function. But you can still give a name to it. For example, I give a name to it. I call it add, and then I call it directly. 10 plus negative 10 is 0. So later on, in future lectures, you will see examples where Lambda functions are called without a name. So it is just wrapped in some code and without a name at all. You don't have to give a name to it. So the Lambda function is roughly equivalent to the following function defined by the def function or keyword. Same thing. So this will be the same function. And this is another example of a Lambda function. So a Lambda function can include conditions using if statements. So Lambda x, this is the only input argument. And then positive, return positive if x is positive, greater than 0, else return negative, right, if x is less than 0, and else 0. So this, let's define this and check the result. So -1, -0, 0, 15, positive. So it's possible to make it a little bit more complicated. So it can take if statement, if, else, and else if. All right. So that's all about defining functions using the def function or the Lambda function. As I said, the focus of our class is not Python programming. So this is just for your information. We rarely need to create a function by ourselves. We rarely have to do so. But it's good to know, right? All right, next topic is list comprehension. So this is a very small, it's a very special thing in Python. So let's take a look. What is a list comprehension? You see in the statement, you have a square bracket. Instead of values, you have some code in it. For I in range 20, if I modulo 3 is equal to 0. So basically, this is a for loop. This is a for loop that will print or filter out those values that are divisible by 3. Right? And this I something is, it specifies the values that will be contained in this list. So this is called a list comprehension. So this is the result. Right? Values from 0 to up to 20, which is 19, that are divisible by 3. Right? So this is the result. From this example, you see that list comprehensions are a way to compress a list building for loop into a single short readable line. So what is a list building for loop? So it's a for loop that can be used to build a list. Okay, and you wrap that for loop into a list and use that to specify or to define the values in the list. So that is, a list comprehension. For example, we can take a look at the following for loop. Create an empty list, call it L, and then for n in range 12, from 0 to 11, L append n to the 2. Right? So you basically want to list n squared for n equals 0 to 12, 11. So let's run this. So this is a list. So using this for loop, you gradually append new n squared values, one after the other, right? And similarly, you can do this. You can create a list comprehension to do the same thing. So n to the 2, so n squared for n in range 12. So this is the for loop that is used to build the list. And the first item in the list comprehension is always the result, the actual values that should be contained in the list. And after that, you have a for loop that can be used to define the values of n, or in this case is a looping variable. See, you get the same thing, right? So this is a list comprehension. Apparently, it's a way to create a list with some patterns, with some type of patterns. And because you use a for loop, you use a loop in it, you avoid you avoid repetitions, and also you can save the list with, it will save memory. Okay? Because instead of, for example, if this is a very big range from 1,000, if you list the entire list, it will be very big, right? But if you use this code, it will be the same length of this. You make it 1,000, right? The code is the same, right? But the actual list is much longer, right? All right, so this is a list comprehension. All right, so that's all for this class. So this is a regular, this is the syntax for a list comprehension, right? Square brackets, and then expression for some looping variable in iterable. Iterable is any iteration, right? Any code that you want to execute in each iteration. And this expression must be a function of the variable, must be the function of the looping variable. Otherwise, the for loop won't have any effect on the expression. It doesn't make sense, right? So this is the standard syntax of a list comprehension. All right, again, it's good to know, but we won't use it a lot in our class. All right, any questions so far? Questions? Yeah. Then let's move on to sessions 1.6, loading data. Again, this is a kind of trivial, but still very important topic. Over the years, I found that some students couldn't load data properly even at the end of the semester. So they lack some basic skills. So it's good to make it very clear at the beginning of the class. So loading data in Python. The first step in machine learning is to get the raw data into our system. In this session, we'll talk about loading data from a variety of sources, including CSV, Excel, and JSON, and also generating simulated data with the desirable properties for experimentation. simulated data. And lastly, the pandas and Scikit-Learn packages. So almost all of the packages in Python have their built-in data sets. Also take a look how to load their data sets. So we start from the third item actually, loading a sample data set. So sometimes before applying your machine learning model on real data sets, you want to experiment it using some toy data set first. And some Python packages have built-in data sets. They are clean, and usually the size is manageable, not too big. And also they are very kind of neat data sets. Let's take a look at Scikit-Learn's data set. Scikit-Learn has 3 very useful and popular sample data sets. The first one is load Boston. This one contains some variables about Boston housing prices. It's good for regression problems, regression models, because the response variable is numeric, is median house values. And then the second data set is load iris. This one contains 150 observations on the measurement of iris flowers. This is good for classification problems because the response variable is categorical. It only has 3 categories, 3 types of iris flowers. And the last one is load digits. This one has about 1,800 observations from handwritten digits images, processed images. And this is good for teaching image classification. So in our class, I think we will use all of these. Let's take a look at load digits first. The load digits has handwritten digits images. So let's first load it. It takes a little bit. So first import the dataset submodule from Scikit-Learn, and then load the specific datasets using this and call it digits. So this digits is a very comprehensive object. It contains different components. And one component is the data component. So this is the features matrix, which only contains X variables. And then the target component contains the response variable. Usually it's just a vector of values. Okay? So it is the Y variable. And lastly, we can take a look at the shape of these 2 parts using the shape method. So the features matrix has 1,797 rows and 64 columns. It's a very wide data set with 64 columns. So all of them are actually, the features matrix are used to define the image. It's somehow like this. Given an image, it is separated to 64 little squares. Okay. So decompose in this way. And so total like 8 by 8, so 64 feature variables. Each variable is corresponding to the grayscale of one little square between 0 and 15. So 0 is white and 15 is solid black. Any number that is in between is a certain shade of gray. Okay? The larger the number, the darker the gray is, the gray color. So you understand that, right? So that's why the features matrix is very wide. It has 64 columns. And totally you have these many rows. And then let's take a look at the shape of the target variable, the response variable. It is a one-dimensional vector with these many observations, which makes sense, right? All right. Now let's take a look at the first row of the features matrix. That's to take a look at the features variable values. And indeed, they are from 0 to 15, so they are all grayscale, representing grayscales. And the target variable, let's take a look at the response value. So this is the first number, the true number of the first digit image. It is 0. The first number is 0. And let's plot it. Let's plot the first observation, the features matrix. So see, this is a 0. This is a handwritten digit 0. Of course, this is originally it was an image, like a picture, but it is processed in a way that is simpler and smaller. The size is smaller and easier to understand, to be understood by a computer. Okay, so it's a processed handwritten image. And you can tell it's a 0 very easily, right? And in the digit image classification problem, you try to train your machine learning program to recognize numbers from handwritten images. Right? Our human eye, for us, is very easy to tell, but computers don't have eyes. They have to tell from the numbers, right? Namely the features matrix. Right? So you have to train them to correctly identify digits from images. So that is the first toy data set, log digits in Scikit-Learn. And then let's move on to the second topic, creating simulated data sets. Sometimes it's very useful for us because you want, for example, we have some algorithms, we want to test if it is good or not, it is appropriate or not. We want to simulate some data. Simulated data are controlled. You have the full control of the response variable and the feature variables. And you know exactly what coefficients are in the model. So it's better, it's easy for us to assess our model. You have, you know the truth. So it's easy to evaluate your model. So let's first take a look at creating data sets for regression. You can use the make regression function. Take a look at the following example. So first load the make regression function from Scikit-Learn's dataset submodule. And then let's see how to call the function. I just make regression, specify some arguments. Okay. N samples is used to specify the sample size, how many observations in your data set. And N features, so this is the width of your features matrix, how many columns of X variables in your simulated data. And then N informative, this is the number of features used to generate the target vector. So this is the number of X variables that are actually used to build Y. For example, in a regression, Y can be, the true model maybe is this. Okay. In this case, N informative should be 2. And informative should be 2. However, you may specify a larger features matrix, namely you add one useless column in the features matrix. That will be good for testing your model selection process. Right? model selection or tuning process. Right? So pay attention. So any informative specified variables that are used to generate a target vector. And n targets usually is 1. That means you only have one y variable, but it's possible to create multivariate regression data. For example, you have paired y variables, the height and width of an object, etc. is possible. And noise, so this is the mean of the error term. So epsilon in regression. Usually in regression, we say the mean of epsilon is 0. So noise equals specify the mean of epsilon. And coefficient equals true. If you set it to be true, then the algorithm will return the coefficients of the underlying linear model. Just as I just showed you, suppose the true model is like this. So this beta 0, beta 1, beta 2 will be returned. Okay, if you want, you can extract this information. Usually, they are very useful because after you fit a regression model, for example, you want to compare your estimated coefficient estimates with the true coefficients. Using least square, you will have solutions for all of these coefficients. Then you can compare with the true. All right. So now let's do it, and after we do the simulation first. Oh, by the way, the result is comprehensive. It's kind of like a list of objects, and you can save them specifically. Like the first is features matrix, and then the target vector, and last one coefficients. So this one contains the values of coefficients because we set coefficient equals true. The true coefficient will be saved in this part. Okay. And then let's print out the first 3 rows of the features matrix. So 3 rows. And each row has 3 components because n features equals 3. You have 3 x variables. And then true coefficients. So these are beta 1, beta 2, and beta 3, not including the intercept. So beta 0 is not considered as a coefficient in Python. Pay attention to that, because this is different from R. In R, the intercept is considered as a coefficient, but in Python, only slopes are considered as coefficients. And the intercept is called a bias, the bias in the model. Is called the bias. So it has a different name. And last one, we print out the first 3 values in the target variable, target vector. So this is y1, y2, y3, the first 3 observations. Okay. Yeah. Next, classification. Sometimes you want to evaluate your classification model, which means the response variable is categorical. So it is not a numerical variable anymore. It is a variable with category labels. So let's see how to do it. So first, import the make classification function from this submodule, and then specify some arguments and samples the number of observations, number of features. So these are the same. And last one, n redundant is equal to 0. So this one plus this one should be equal to this. Okay. So the number of redundant variables plus the number of informative variables is equal to the total number of features in the matrix. Right. So this is not necessary. You don't have to specify it. I listed here because I just want to show you that this argument is available. And then n classes. So this is the number of categories for your response variable. Suppose I want to make it a binary variable with only 2 values. So by default, it will just use 0 and 1 to represent the 2 categories. And then the weights vector is used to specify the proportions of each label. Right? So 0.25, 0.75 means in the data set, 25% of the y values should be 0. 75% should be 1. Right? So you can create unbalanced data. If you don't specify this, then it will make a completely balanced data set. 50% 0, 50% 1. And lastly, random state equals 1. So this one is used to specify the random seed when you do the simulation. Essentially, this is a simulation, right? So to have reproducible data set, you can set this and save the result in features 2, target 2. So notice that I didn't specify a coefficient equals true, so I will not return the true coefficient. Usually in classification problems, the coefficients are not so important because the relationship is not linear anymore. The relationship between y and x variables is not linear, so you cannot make direct connection between x and y. Consequently, the betas, the coefficient estimates are not that important. So let's take a look at run this first. And then let's print out a few rows, like the first 3 rows of the feature matrix, and then the first 3 values of the target vector. Because we made it binary, the values are either 0 or 1. Right? If you specify it like 3 classes, then you will see 2. Some values will be equal to 2. All right, we have done this. And the last one is clustering. So clustering is an unsupervised learning problem. When you don't have a target variable, you don't have a response variable, you only have a bunch of features variables, and you want to figure out patterns or relationship among those observations or data points in your data set. So this is usually called clustering, a clustering problem. And Scikit-Learn also has this make blobs function that can be used to create simulated data for clustering problems. The function is called make blobs. And then some arguments are similar, n samples, n features, and then centers. So this is the number of groups or clusters in your simulated data set. For example, 3 means there are truly 3 centers. And then cluster standard deviation. So this specifies the variation among the observations within each cluster. The in group or within cluster variation. The larger the number, the bigger the cloud, the radius of the cloud of each cluster, if it's 2-dimensional. And last one, random state. Let's run it, and then let's visualize it. Let's first take a look at the first few rows. Oh, by the way, although this is a function that is used to create data for clustering problems, the true membership will be created for you, can be returned for you too. Because there is a grand truth still, because you you use simulation, you know exactly which cluster each point belongs to. Okay? So that is called the true membership of a cluster. So that's the advantage of using simulated data. Right? You know the true membership, right? And then if you fit a clustering machine learning model, and then you can compare your result with the true membership and evaluate your unsupervised learning model. So in practice, in real world, you use real data. There is no target variable. There is no true membership. So you cannot evaluate your model in this way. Anyway, let's take a look at, let's create a scatter plot for the data we just simulated. So we specified 3 centers, so apparently 3 groups. And the standard deviation, the cluster standard deviation is 0.5. So see, in this case, they won't overlap much. I think if you set standard deviation equals 1, it will be kind of larger. So the larger the standard deviation, the within cluster standard deviation, the more difficult to cluster them in a precise way. You can imagine if the cluster standard deviation is very large, then they may overlap. Right? They are not separable. Then we cannot avoid making errors, prediction errors or clustering errors. So it's more and more challenging with larger and larger standard deviation within clusters. And we can optionally map the true membership to the points in the scatter plot. You just need to specify C equals target. So this is the true membership, and you map it to color. So in module 3, we'll talk about data visualization, and we will see more details about creating plots. For now, we'll just illustrate the simulated data. And we graphically display the simulated data and you know how they look like. All right. And then next, loading existing data sets, real data sets. So in our class, we will talk about just 3 types of data files. The first one is CSV. CSV stands for comma separated V. I don't know what is V, but the CS stands for comma separated. So by default, the separator is comma. So we can use pandas read CSV function to load a local or hosted CSV file. A local means you have downloaded the dataset and saved it in your local folder. Okay. Oh, okay. Thank you. Yeah, Grace told me that a V stands for values. Thank you. Yeah, that makes sense. Okay, comma separated values. Okay, thanks. And we can use pandas. Pandas is a package. Okay, you can use it to load local or hosted. Hosted means it's an online data set, right? Online hosted. So now let's see how to use it. First, import the pandas package, call it PD. And so this is a conventional alias for pandas. And then we specify the URL of the data set that is hosted online. And then you can just directly call the function pd.readCSV and parentheses the URL. Save it here, call it data frame 1. So from this code, you see that this function readCSV has some arguments with default values. You don't need to specify them, but the only one that you need to specify is the source that you use to load the data. Right? And the head function will show the first few rows. Let's see. So this is the first 2 rows of the data set. Okay. All right. And let me see. CSV files by default use commas as separators, but sometimes you may see CSV files with other separators, for example, tabs or semicolon, etc. In that case, you can use the SEP argument to specify the separator. For example, if it is semicolon, you can just say SEP equals quote semicolon. And also, it assumes that the CSV file you read in has column names, and the first row contains column names or headers. So this is a default assumption. If you don't have a column, so if the CSV file has no column names, then you just need to specify header equals none. Then it will read the data line from the very beginning. Later on, you can add column names. So if header equals none, then Python will give some column names for you, for example, x1, x2, etc. And you can change the column names by yourself later. And you can also import a local CSV file. So in this case, you just need to specify the class of your, the directory of your data set that you saved in your own local folder. For example, the Apple quality data set is saved in my data folder in this, the same, the path is like this, and then I can read it in. Alternatively, if you put the data set into the same local folder with your Jupyter notebook, then you can omit the path and only specify the file name, applequality.csv. So how to put it into your local folder? One way is to upload it to your Jupyter this window. Okay. So how to do it? Just click upload, and then try to find the data set you want to upload. So I need to upload this one, Apple quality. Okay, and click open, and then upload. Oh, yeah, it's already exists. Upload, and then you see that Apple quality is uploaded here, right? So it's in the same folder with my lecture notes, which is here, right? In the same folder. If it's in the same folder, then you can load the data set without specifying the directory. You are only to specify the file name. So this is another way to import a local data set. And sometimes you want to import an Excel file. Excel files are similar to CSV files, except that Excel files may have multiple sheets. You know that in Excel you have sheet 1, sheet 2, okay? You may have multiple sheets. In this case, you need to specify the sheet name or sheet index. And also, you need to specify whether or not it contains headers. For example, the function is just called read_Excel, similar to CSV. And specify the URL, specify the sheet number, sheet name. You have 2 ways. You can specify the index. 0 means the first sheet, okay? And 1 means the second sheet, etc. You can also specify the sheet name, quote sheet name, the true sheet name. And then header equals 0 means the first row contains headers or column names. 0, remember Python is zero-based, zero-indexed, zero-based indexed. Okay? So 0 means the first row. Okay? So let's run this. And you see, we can read it this way. Okay? Headers here is the first sheet. Some more notes about it. It's possible to load multiple sheets at the same time. Okay? You just need to wrap those sheet indexes and sheet names in a list. You see sheet names equal this. You can do this. Okay? Just pay attention. The sheet name must be exactly the same with the real sheet name. Okay? And yeah, so that's it. So last one is JSON. So this is a special type of data, but commonly used. It's also possible to import a JSON file. And yeah. So I rarely use this type of data set actually. So I won't talk too much about it. If you want to know more, you can read the slides and search online about it. But there are some small differences between pandas and other recipes. All right, so that's all for loading data. We talked about loading sample data sets from packages in Python, different packages. So today we only talked about data sets in Scikit-Learn, but actually all the packages have almost all of the packages have their own built-in data sets, like Seaborn, which is for visualization. It also has the iris data set. And also pandas. Pandas also has some data set. It also has the iris data set thing. Iris is a very popular data set. And just pay attention, for different packages, data sets are stored in different formats. And consequently, when you load the data set, you might need to use different functions and pay attention to the structure. In Seaborn, for example, the target vector and the features matrix are together. I think they're together. They are not separately stored. And also in pandas, all of the data sets are pandas data frames. So X and Y are also together. And in machine learning, we use Scikit-Learn to do machine learning usually. And machine learning functions assume that X and Y are separate. Okay, so you need to split them. If you load the data set from, for example, Seaborn or pandas, you have to separate them. Okay, but anyway, a lot of stories. We will talk about them in details when we use those data sets. And the very last topic today is special topics. Again, they are quite useful, although sometimes we ignore them. So first are errors and exceptions. So if you have started working on your homework, you probably have encountered some error messages. So in Python, there are 3 types of errors. The first one is syntax error. So these are errors where the code is not valid in Python. So basically, you didn't follow the syntax correctly, and your code is wrong. So this is easy to fix usually. You just need to carefully check your code and compare it with the correct syntax, and you should be able to figure it out. For example, you are supposed to use parentheses, but you forgot, or you are supposed to add a comma here, you forgot. It's easy to fix usually. The second type is runtime error. So in this case, errors are syntactically valid, but it fails to execute. Okay, so in grammar, your code is correct. However, it does not run. In that case, usually it's because of invalid user input. For example, the function only takes numbers, but you input a character string, etc. So sometimes easy to fix, sometimes difficult. And the last type is semantic errors, errors in logic. So this is the most difficult to fix because the code executes without error, without the problem. You might not notice that. However, if you carefully examine your result, you'll see that your result is not expected. It's not consistent with your expectation. In that case, there must be something deep in your code that is wrong, guys. Logical errors, difficult to fix. So today we'll just talk about runtime errors, a few types of runtime errors, because they are kind of, you can summarize different types of runtime errors. But for the first type and third type, it's very difficult to summarize them into a few common types, right? Because they are kind of case by case. And first runtime error is you reference an undefined variable. So this is quite common for beginners. It's, for example, I say print Q, and then I will get this error. Name Q is not defined because Q hasn't been defined yet. It does not exist. Of course, you cannot print it. And next one is try an operation that is not defined. If you try to add 1 to ABC, then you get type error. Unsupported operand types for plus, integer and string. So this is very easy to fix too. Next one is compute a mathematically ill-defined result. For example, 2 divided by 0. You get this 0 division error. So whenever you do something like this, you will get this message. Last one, try to access a sequence element that does not exist. So L is equal to 1, 2, 3, a list. It only has 3 values. If you want to extract the 1000 component, you'll get this result. It's an error. So these are runtime errors. So usually Python will not only indicate that there is an error happened, it will tell you something about the error, a meaningful exception. And you have the option to raise your own exception. It's very useful to raise some errors if the input is invalid when you create your own functions, right? For example, in the Fibonacci function, we create a function like this, right? And if the input is invalid, for example, we assume that the input is a positive integer, right? Positive integer, because it's the number of Fibonacci numbers, right? But what if they input a negative number? Then you should remind them that your input is invalid, right? So that is the reason that we want to raise a value error. You can do so. So for example, when the input is 10, it's okay. When it's negative 10, yeah, a value error will be raised. So it's a good way to handle invalid inputs. All right, the very last topic, modules and packages. This is sort of a common topic, commonly sort of important topic, but also sometimes we ignore it. How to import packages. The first one is the import, using the import statement by itself. So this one is the best option. So this is called explicit module import. So if you import a module in this way, then the module's contents will be saved or preserved in a namespace. Right? So they are put somewhere. Okay? However, they are not directly available for you. If you want to refer to a function in the module or package, you have to say which package you are talking about. Right? The function is contained in. Right? So that's why you always need to use this period, this dot syntax to connect the package and the function. So for example, we import math package, and then we can use everything in the math package, but we need to refer to the package each time we call a function or a constant in it. For example, we want to calculate the cosine of pi. Then we do this math.cosine parentheses math.pi. Okay. So this means both of the cosine function and the pi constant are contained in the math package. So this is called explicit module import. And sometimes because the package has a very long name and we want to save time, we can give an alias to it. We often do this for NumPy, we call it NP, for example. And then we can calculate the cosine of pi using the cosine function and the pi constant in the NumPy function. So from these two examples, you see that different packages might have same functions, even with same names. So that's why this type of import is good. It's explicit. You know exactly which package a function belongs to. Because sometimes a function has the same name in different packages, but the argument and usage and purpose is different. So if you use implicit import, then everybody will be confused. All right, and the next one is explicit import of module contents. So this is the second type of import, second way to import items. So in this case, in this way, we will import specific items from a package. So that's the from, we use from the package import items. Right? So if we use this method, then we can directly call the function and the constant in the package without referring to the package. So you see, the syntax is simpler actually. So it is okay, but not as good as the previous one because, for example, if you have a very long chunk of code, later on, you might forget which package this function is from. If your code program is very short, it's okay. Anyway, it's at least is traceable, it's tractable. You can go up and flip a few pages and see that, oh, these two are from this function, this package. Okay, it's okay, we're sure. So it's still kind of explicit, although you don't refer to the library anymore. The worst one is implicit import of module contents. For example, from math, import asterisk. So this means I will import everything from the math package. And by doing so, you import everything, but you're not sure what are exactly contained in the math package. So it still works. However, there is a risk that you might override some functions or items or constants that you don't want to override. So that is kind of risky. And also because it's implicit, everything is implicit. You are just not sure what's going on, what are available in your workspace currently. So you should try to avoid it, avoid this type of import if it's possible. All right. And lastly is third-party libraries. Sometimes, of course, because you have Anaconda installation, you have most of the packages you need in this course. But sometimes you might want to install some third-party packages. In that case, we have a very convenient way to create it in Jupyter. It's called the pip installation. For example, if you want to install a package called Super Smoother, you can just create a new cell in Jupyter. Just type pip install Super Smoother and run the cell. Then this package will be installed and available to you. Then you probably need to save and quit Jupyter and reopen it. Okay? And then it should be at work. You can start to use this package, any functions in this package. Okay. All right. Perfect. We are done with other sections in Python basics. And next time we'll talk about data management. Start to talk about data management. Hopefully we can use 2.5 lectures to finish the next module. All right, that's all for today. We'll see you tomorrow. If you have